the plan for today is that we will, I will first say a few things about one of the questions that was asked yesterday, and to which I think I have a better answer than the answer I got yesterday. Then we're going to talk about the Boltzmann equation that describes sterile neutrino production in the early universe. And then we're going to talk about sterile neutrino constraints. Now, first about that question that was asked yesterday. So this was in particular about this integral over the observation time that we did when computing the neutrino oscillation probability. So if you remember, we had an expression that looked like T alpha beta equals some alpha beta. Then there were all these matrix elements, and then we had the exponential factor e to the minus I ej minus ek times t plus I dj minus pk times L. And then we argued that in a typical neutrino experiment, this time t here is not measured, and therefore we integrate over it. And then someone asked an excellent question, namely, what is that like in neutrino beam experiments, where we know relatively precisely when the neutrino is produced because the beam spills are short, and we know when the neutrino is detected because our detectors have good timing resolution. And the answer is that even in those experiments, it's still justified to do this integral. So the typical time, let's assume the time resolution that you achieve, let's call it delta t, is of order nanoseconds. A nanosecond is something like order 10 to the minus 7 inverse EV. On the other hand, the first factor, the ej minus ek, that is typically of order delta m square over 2e. Now delta m square is 10 to the minus 3 ev squared. E is maybe gev squared. So that's a number of order 10 to the minus 12 ev, say. And to show that this is the right expression for the energy difference, you can, for instance, do an explicit calculation for the case of pi on dk. So you see that by integrating even over a short time interval of order a nanosecond, we are still integrating over many, many, many oscillations of this first exponential factor here. And because we're integrating over so many oscillations, this will only give a contribution when ej minus ek is really close to 0, and therefore it's justified to extend the integral over the whole time domain from t equal minus infinity to plus infinity. And that's what justifies the approach that we took yesterday. So that just as an addendum to what I explained yesterday, but I think I should have explained better. Now let's come back to sterile neutrino production in the early universe. We had considered the Boltzmann equation, which look like this, d over dt minus h times e times d over de of the sterile neutrino phase-space distribution. And we took that phase-space distribution to depend only on energy and time by invoking the isotropy and homogeneity of the universe. Now, this is equal to a collision term, which had the form 1/2 sine squared 2 theta m of E and T times gamma of E and T times the phase-space distribution function of the active neutrinos, which we're going to denote Fa of E and T. Okay. I've also given you explicit expressions. So Fa was taken to be just the Fermi-Dirac distribution because we neglect any feedback of these oscillations on the active neutrino population. So we assume they are just in thermal equilibrium. For this scattering rate gamma, we had an expression that was proportional to the Fermi constant squared times the temperature to the 4th times the energy. because this is just a weak interaction. So there are two, there's one weak interaction vertex, which gives a factor GF. It gets squared when computing a rate, so GF squared, and then the other factors are there to set the dimensions right. Okay. And we've also already discussed the physics of this first term. Let me quickly check what was the last thing we did yesterday. Yeah, we've already done this. I've argued that the first term in the equation is just the total time derivative of the sterile neutrino distribution, which depends on the explicit time derivative, so the partial time derivative, and a term that describes how particles are moved from higher energy bins to lower energy bins due to redshift. Okay, so that's the equation that we have to deal with. And the next step that we are going to take now, and this is now where the new things start. So we are going to integrate over momentum. So integrate over d3p over 2 pi cubed. The reason we are doing this is when we integrate a phase-space distribution over momentum, then we just get a number density. So we are going to introduce the number density, which is ns of t, so the sterile neutrino number density is 2. There's a factor of 2 because there's particles and antiparticles. Integral d3p over 2 pi cubed times fs of E and T. The other thing we are going to do is we are going to go from derivatives in T to derivatives in A, because A is like the, so by A I mean the scale factor of the universe, because A is in cosmology a somehow more easily tractable quantity than actual physical time. So we go from d over dt to d over dA. So where does this lead us? The derivative of the phase-space distribution, the number density of S with respect to the scale factor is, well, it's the derivative of the integral that I just gave you here. Integral d3p over 2 pi cubed fs of E comma t. So at the, I'm just plugging in the definition of the number density. Now, because the number density depends on energy, we are going to replace momentum by energy, and we're once again going to use isotropy, so we don't have to worry about the angular integrals. So this is 2 times d over dA, integral 4 pi E squared dE divided by 2 pi cubed times fs of E comma t. Okay, now comes the more non-trivial step. Now we pull this derivative with respect to A into the integral. And the result of this step is the following. I'm going to write down the result and then we're going to discuss it in a bit more detail. 2 over A dot times integral 4 pi E square dE over 2 pi cubed times the partial derivative of fs with respect to t. Then there is a term minus 2 times integral 4 pi E square dE divided by 2 pi cubed times E over A times the derivative with respect to energy of fs of E comma t. So the first term, the first term here arises by applying the derivative of A, well, by using the chain rule of the derivative and taking the partial derivative of s with respect to t, and then we need to differentiate dt over ds. That gives the 1 over a dot. Similarly, we also need to take the partial derivative of fs with respect to e, and then compute dE over dt. That gives this factor e over a. And now there is a third term, because also the energy that appears here in the integration measure depends on the scale factor. And this additional term has the form -6, because there's 3 factors here, 2 factors of e and 1 factor of dE. So -6 times integral 4 pi e squared dE over 2 pi cubed times e over a. That's once again the time derivative, the a derivative of e. So e over a times fs of e, comma t. So once again, to write this out explicitly, what I just said. So this comes from the derivative with respect to a acting on e square dE, and using that dE over dA is just e over a. Oh, no, wait, is sorry, is this right? Is so we can write the energy as some reference energy times divided by the scale factor, and this means dE over dA is equal to minus E0 divided by a square, which is minus E over a. And so here this should be dE over dA is minus E over a. Right, so we're using the fact that the energy scales with the inverse scale factor. That's just a statement of redshift. And when we take the derivative with respect to a, then we just get minus E over a. So this is where this minus sign here is coming from, and this minus sign. The minus sign in the second and third term are coming precisely from there. Okay, so that's now the most cumbersome expression we are encountered today. From here on, we'll be able to simplify. The first step of simplification is that many of these integrals that we have here now, well, they are just, can be rewritten in terms of ns, or some of the a dots here can be rewritten in terms of the Hubble constant, but let's do this one by one. So the left-hand side stays unchanged. Let me only multiply the whole equation by a dot. dns over dA is equal to 2 times the first term. So that one we leave unchanged for the moment. We've just removed the factor of 1 over a dot because we've multiplied the whole equation by a dot. So partial derivative t of fs of e comma t. The second term, when we multiply by a dot here, we get a factor of a dot over a, and that is just the Hubble parameter. So we introduce the Hubble parameter. So minus 2 times integral 4 pi e squared dE over 2 pi cubed times Hubble times E times the energy derivative of the phase-space distribution. And finally, the last term, the same thing happens when we multiply by a dot. well, A dot over A turns into Hubble. The rest of the integral turns into the number density. And this is mostly the case because I made a typo here. So here, when I take remember that the last term here comes from taking the derivative of the integration measure. Obviously, when I take the integration measure, one of the powers here should go. So this 2 should be gone. So with this correction, what I have here, the new integration measure is just, again, 4 pi e squared dE over 2 pi cubed times fs, that is the number density, and the factor a dot over a can, of course, be pulled out of the integral. So this last term turns simply into -6 times Hubble times ns of e comma t. So that one at least simplifies already at this step. No, I still have I have a 6 here. That does not.
Yeah, because
oh, you're right. Yes, you're right. Because I absorb a 2 into the definition of ns. Yeah, good point. Okay. So now what we have here in the first 2 terms, what's under the integral here, is very similar to what we had on the left-hand side of our Boltzmann equation. If you allow me to quickly scroll up again, here we also had d over dt minus he d over de. So that's precisely what's appearing under the integral here in the first 2 terms. So in those first 2 terms, we can now apply our Boltzmann equation. So we use the Boltzmann equation. And with this, well, the left-hand side stays unchanged, a dot times d over dA of ns. The term with the 3h ns is going to be brought to the left-hand side. And here I also made a stupid mistake. Obviously, ns does not depend on energy anymore. It's just a function of time, or a, depending on what you prefer. And for the terms on the right-hand side, we apply the Boltzmann equation. So we can replace the dtfs minus he d over defs by 1/2 sine squared 2 theta times the rate. This is something that can be pulled out of the integral. And what remains is once again just the number density. So the prefactor, I'm going to abbreviate this as little gamma times NA. And this thing that I call gamma here, this is equal to 1 over NA times integral d3p over 2 pi cubed times sine square 2 theta m of e comma t times the interaction rate at E and T, times the phase space distribution of the active neutrinos, E to the E over T plus 1. Right, so this all comes from inserting the Boltzmann equation. And well, because I want to, I'm normalizing out a factor of NA here to basically be insensitive to the overall number density of NA and more to their spectral shape. It's just a matter of how I write things. Okay, so this factor here still looks relatively complicated. However, this does not depend on any unknown anymore. So it does not depend on the phase-space density of stereo neutrinos anymore. These are all essentially quantities that can be computed in the standard model. The mixing angle, the rate, well, and there's the Fermi-Dirac factor. So this is something that is just a number that we can compute. Okay. Now, one final step we can take is that instead of writing an equation for the number density ns, we can turn this into an equation for the ratio of sterile to active neutrino number densities. That will have the advantage that sterile neutrinos and active neutrinos are redshifted in the same way. So the goal here is to get an even simpler equation in which the redshifting factor does no longer appear. So we can turn this into an equation for a quantity which we are going to call R and which we're going to define as NS over NA. If we want to do this, then we need to know the derivative of A. So by using d over dA of NA, and that's just minus 3 over A times NA. That just comes from, it's easy to show, it just comes from the fact that active neutrinos are basically redshifted, and that's all that happens to them during this period of cosmological evolution. Okay, so with this, we obtain that A dot times d over dA of R plus A dot times R over NA d over dA times NA plus 3H dot R is equal to gamma. That's equivalent to just saying that A dot d over dA of R is equal to gamma. Oh, sorry, I didn't see the question. Yes.
So when we make this approximation for active neutrinos, this means that we're considering a moment where they have already decoupled the active neutrinos, right?
We assume a moment where they are still in thermal equilibrium, but they still have an appreciable scattering rate. So they are freely produced and absorbed by the thermal bath. So they always follow a Fermi-Dirac distribution. What we are neglecting is the fact that a few of them are disappearing into sterile neutrinos. So there might be momentarily, there might be a tiny out of equilibrium situation because a few sterile neutrinos a few active neutrinos have been converted into sterile neutrinos, and it may take a few moments to recreate them from other standard model particles. That's what we are neglecting here. But since the final fraction of sterile neutrinos that we are aiming for is of order 10 to the minus 10, that's a totally negligible effect.
Okay, I see. And another thing, maybe you already suggested about what does determine the mixing angle in matter? That does in a few words. What does it make it different from the mixing angle in vacuum?
Mm-hmm. So the reason it makes a difference is when you consider the Hamiltonian that describes neutrino oscillations. I'm going to write this down and then erase it again. The Hamiltonian that describes neutrino oscillations in vacuum has this form U times 0. Oops. Come on. Hey. Hey. Oh no. Now back to the usual pen. Delta m square over 2e times u dagger. So that's basically the Hamiltonian that describes flavor evolution in vacuum. Now, if neutrinos travel through matter, they can exchange W and Z bosons with the material. Z boson exchange is irrelevant to the flavor evolution because it's exactly the same for all neutrino flavors. However, for W exchange, you have diagrams of this type. You have an electron going in and a neutrino going in, going to a W boson, and an electron and a neutrino coming out. This is a process that exists only for electron neutrinos, not for mu and tau neutrinos, because there are no mu's and taus around anymore. Now you might argue, okay, the neutrino scattering rate is low, so why do we care? The thing is that there is a kinematic region where this process can happen with zero momentum exchange. So the initial and final state particles are in the same quantum state, even though a W boson has been exchanged. Now, in this case, you have no way of telling which of the many electrons in your background matter the neutrino has interacted with. And therefore, you have to coherently sum over all of them. And this coherent sum over all the scattering targets along the way gives a huge enhancement. And therefore, these diagrams are relevant even though neutrino interactions are extremely weak. That's called the Mikheyev-Smirnov-Wolfenstein or MSW effect. And the way it shows up is an extra term in the Hamiltonian, which basically has the structure V, and I can tell you what V is. It's square root 2 times G Fermi times the electron number density and 0. So you're now bumping up one of the diagonal elements of your Hamiltonian. And when you have a nicely mixed system and you're bumping up one of the diagonal elements of the Hamiltonian, what this effectively means is that the mixing angle that diagonalizes this Hamiltonian becomes smaller. And that's why the presence of matter affects neutrinos. Now, in the early universe, the situation is a bit more complicated because in the early universe, it's not really diagrams of this type that are all that important, and that's because there are equal numbers of electrons and positrons, and they give equal and opposite contributions. But there are additional diagrams which, when evaluated at finite temperature, do give a contribution. That's the same for neutrinos and antineutrinos, and therefore do not cancel. And that's the reason that we have to worry about this in the early universe. Sure. Thanks for the question. Okay, now just some minor rewriting that we can still do if we want to. Well, we can write A dot as A times Hubble, leaving the rest unchanged. And with this, we can write the left-hand side as dr divided by d ln A is equal to gamma over h. And that's the final form of this equation that I had been aiming for. So the you see that this exercise of normalizing the sterile neutrino number density to the active neutrino number density, it just has the advantage that the equation now has fewer terms, but one can work just as well with the equation that we had previously. One caveat that I should mention is that as the universe evolves, from time to time, particle species freeze out. This is an effect that I have neglected here, because whenever a particle species freezes out, the energy contained in that particle species gets injected into the remaining particle species, which leads to a slight slowdown of the expansion. That is an effect that I've neglected here. It can be included relatively straightforwardly. It leads to an extra term here that contains the derivative of the effective number of degrees of freedom. But for our purposes, this equation is perfectly sufficient. So what this shows you is that, first of all, like so many things in cosmology, this is a process that's happening on log scales. So the rate of production in each decade of scale factor is the same, or roughly the same. And it's given by, well, this rate that depends on the mixing angle and the scattering rate of sterile and active neutrinos. And graphically, what we expect as a function of the scale factor, well, let's say log of the scale factor, where the sterile neutrino number density will initially be small, just because there hasn't been enough time for neutrinos to oscillate, and then it will grow to a certain value and eventually will cease to grow. So at very early times, well, there hasn't been enough time for neutrinos to oscillate, and the effective mixing angle is extremely small because these new terms that appear in the Hamiltonian because of the presence of matter are very, very large at very, very high temperature. So the effective mixing angle is small, which means also the oscillation amplitude is suppressed. Then at some point, there's like a sweet spot. This sweet spot happens at maybe around 100 MeV or so, between 110 MeV roughly, where the mixing angle becomes sufficiently small and the scattering rate is still sufficiently large for this production mechanism to work. And then at later times, the production rate is too low. So here we have low gamma. Here at early times, we have low theta m. And in the middle, there is this sweet spot where the two counterbalancing effects are just such that production can happen relatively efficiently. Now I'm calling this a sweet spot because it allows for the production of sterile neutrinos. It's not a sweet spot when you want to do a precision calculation, because 100 MeV, that's right where the QCD phase transition is happening. So the background matter behaves in a very, very complicated way. All the hadronic states freeze out one after the other. The effective theory, which describes the particle physics in your universe, changes from a theory involving quarks to a chiral theory involving nucleons. So for a precision calculation, it's a nightmare. But for the mechanism to work, it's kind of nice. Okay, so this concludes our discussion of sterile neutrino production in the early universe. Do we have any questions at this point? I see someone wrote something in the chat. Ah, no, it was just Marcus, then we will begin very soon. Okay, yeah.
So is this process what leads to a delta N effective of 1 for this sterile neutrino? Because it leads to fully thermalized. No.
If it led to full thermalization, then it would lead to delta N effective of 1. If we want sterile neutrinos to be the dark matter, then the mixing angles need to be sufficiently small that that never happens. If you invoke sterile neutrinos, for instance, to explain anomalies in oscillation experiments, or so where you need much, much larger mixing angles, then the process is so efficient that it indeed leads to thermalization and then to problems with the ineffective constraint. But for sterile neutrino dark matter, we really want this just to be a freeze-in, so which means we produce a small number of sterile neutrinos and then the process stops. It never reaches thermal equilibrium. But that's a choice that we need to choose the parameters in such a way that they never reach thermal equilibrium, because otherwise it wouldn't work. Otherwise we would overclose the universe.
Okay, so the delta N that we achieve with that is around 0 point something maybe, or
the delta N effective associated with that is of order 10 to the minus 10.
Okay.
That's just because the energy density of dark matter over the energy density of standard model matter at these early times is of order 10 to the minus 10 or so. Remember, that's also true in WIMP models. For instance, WIMP freeze out requires the dark matter abundance to drop by 10 orders of magnitude or so below the abundance of a relativistic species in thermal equilibrium. So whenever you make dark matter, you need to get this factor of order of something like 10 orders of magnitude from somewhere. Either you start with a thermal species and then you need to get rid of most of them, or you start at 0 and make only a small amount of them. Sure. Okay. So let's next talk about sterile neutrino decay, because that's today the phenomenologically most relevant process, perhaps. So how do sterile neutrinos decay? There is two classes of diagrams, a tree-level diagram and loop diagrams. And what all of them have in common is that they exploit the fact that the sterile state mixes with the active states. So the tree-level diagram is the following. And I should be careful about what I write here. I'm not going to write nu s here. I'm going to write nu 4, so the fourth mass eigenstate. And that's because over cosmological timescales, any coherence that there may have been between different mass eigenstates has been lost. So when we talk about sterile neutrino dark matter, what we actually mean is that the dark matter is in the form of the fourth neutrino mass eigenstate. For the active neutrinos, it doesn't really matter. I'm just going to call this nu A. This means any of the mostly active mass eigenstates. Right, so we have a nu 4, and because that's a mass eigenstate, it has a small coupling to the Z boson suppressed by the mixing angle. So here, there will be a factor of sine theta or so. So it, all bytes suppressed, it talks to the Z boson, and then via the Z boson, it can decay to an active neutrino here, and the Z boson again goes to 3 active neutrinos. So that's a tree-level process. So that's in fact the dominant sterile neutrino decay mode. However, it's very hard to see because neutrinos are very hard to see. And especially remember that we are talking about the keV scale here. So the neutrinos that would be produced that way have energies of order keV. And at the moment, we have no good detection mechanism for neutrinos of such low energies. The rate is just abysmally small. And many detection processes, for many detection processes, it's just exactly 0 at such low energies. And even for processes where it's not 0, it's still extremely small. So the only way this process can be used to set constraints is where we need to require that the rate of these decays is less than the inverse age of the universe, because otherwise there would be no dark matter around anymore, and we know there is still dark matter today. Let's see. Phenomenologically less relevant. Phenomenologically less relevant because order keV neutrinos are hard to detect. But constrained from the requirement that the lifetime, so let's call this tau s, for instance, has to be larger than the age of the universe. So that's one constraint one can set. It turns out that a second class of diagrams gives much stronger constraints. And that second class of diagrams is the following loop diagrams. We have our neutrino line here. So the sterile neutrino goes to a charged lepton and a W boson. And the charged lepton then goes back to an active neutrino. And now I can attach a photon either to the charged lepton line or to the W line. I'm going to show you here only one of those diagrams. So, but of course, there's also the second type of diagram where the photon is attached to the W line. So it's a loop diagram. It contains a loop factor. It once again, of course, contains a mixing angle because this coupling to the W here, that once again comes with a mixing angle. So it does contain a loop factor. It has per se a lower rate, but it produces a photon, and photons are, of course, easy to see. And in particular, it's a two-body decay. So it produces monochromatic photons. And there's few things in the universe that produce monochromatic photons. So this is something that can be relatively easily distinguished from backgrounds, and therefore makes this process quite easy to see. So this process has a somewhat lower rate. But yields monochromatic photons. Now, the rate for this process can be computed. I'm not going to go through the detailed derivation here, but you can already guesstimate the dependence that we are going to have. So there is a W boson here. So probably this is somehow going to be proportional to the Fermi constant squared. But we want to compute a rate. So it has to have mass dimension 1. So something needs to set the dimensions right. And the only mass scales available in the problem are the sterile neutrino mass and, well, the charged lepton mass. So it turns out that the relevant one is the sterile neutrino mass. So this goes as m4 to the 5th power. And there's also the mixing angle, so somewhere there must be a sine square theta. That's roughly the parametric dependence. I know that there must be a mixing angle from this vertex here, I know there must be the Fermi constant because the W mass must enter somehow. Well, and then something is needed to set the dimensions right, and it turns out that this is the sterile neutrino mass. To give you an idea of what the numbers are, this is for Dirac neutrinos, this is 2.73 times 10 to the minus, what's that, 37 inverse seconds times sine square theta times m4 over electron volt to the 5th power. So you see that these are pretty small rates that we are dealing with here. And I should say this is for Dirac neutrinos. For Majorana neutrinos, it's about a factor of 2 different. Okay, so it is a small rate, but nevertheless, this is something that we can in principle observe just because there are so many dark matter particles in the universe, and because they produce this clean signature of a monochromatic photon line. Since we're talking about keV masses, also the energy of that photon line will be in the keV range. So in other words, we are looking for X-rays. So let me write this down. Prediction is an X-ray line from astrophysical objects with a high dark matter density. Objects with high dark matter density. Okay, now, and this is the point where I think it makes sense that I show you some plots. So let me switch the setup a little bit. When I'm opening my slides, I'm still going to leave this on, and then I'm going to switch to the slides in a moment. Stop sharing this, and I probably need to share that whole screen for this to work in full screen mode.
Sorry,
Yeah.
that question.
Please.
So it's still not clear for me why these stereo neutrinos for dark matter candidate need to be in the keV range. Is it just because this is the range that leads to the correct Rayleigh density, or there is a deeper reason?
It's one of the reasons. If you make them heavier, then what hits you is this 5th power of the neutrino mass in decay rate. So very soon they will decay too fast. And if you make them lighter, they are simply too hot. So they don't act as cold dark matter anymore, but they would be hot dark matter, and that's of course excluded. Even in the keV range, I'm going to mention this in a moment. Even in the keV range, they are not really cold dark matter, they are what's called warm dark matter, which is somewhere in between, and which is also these nowadays, this is quite constrained. There was a time where this was actually favored by the data, but now it appears that it's more of a problem than a feature. Okay, so this plot that I'm showing here, it's not completely up to date. I'm going to have a more updated plot on a later slide. It's from 2014, but it gives you an idea of what's going on. So the remote participants may not be able to see where I'm pointing. That's why I'm going to say where I'm pointing. So the horizontal axis here is the mixing angle. And if you look at the scale here, this starts, it goes from 10 to the minus 40 to 10 to the minus 6. So these are really extremely small mixing angles. That's needed because if the mixing angle was too large, we would either overproduce dark matter or it would decay too fast. And the mass range here is precisely the keV range that I promised you. So the red line here on the right-hand side, this line labeled L equals 0, that is the prediction of the Doodles-Vidro mechanism. So just as for axions, we have a relatively stringent prediction of where in the parameter space the sterile neutrino should live if it is made through this production mechanism. However, there's other production mechanisms that also populate other regions of parameter space. And all these contours here that you see there, these are X-ray constraints. So these are observations of X-ray telescopes of various astrophysical objects. For instance, here diffuse X-ray background. This is just integrating over the whole sky, especially in regions where there are no X-ray point sources. You just look at the X-ray flux you get from there. You can use astrophysics to make predictions of what kind of background you expect. And then you see that in order not to exceed this, this background, you can't have sterile neutrinos that live in this light blue region. Similarly here, unresolved CXB, I think it's also cosmic X-ray background at Milky Way. This would be the X-ray emission from the Milky Way. M31, that's the Andromeda galaxy. It's a galaxy, so it has lots of dark matter in it. So we could perhaps hope to see an X-ray signal from there if there was a sterile neutrino dark matter, but we haven't. This region down here, which is labeled the Tremaine gun bound, that's actually an interesting constraint. That's a constraint that comes from Pauli blocking. So sterile neutrinos are fermions, and they are relatively light here. So we're talking about KEVs after all. So in order to account for the observed dark matter energy density, their number density needs to be relatively large. And especially in regions that are known to have a very large dark matter density, like the centers of galaxies or so, this could lead to problems with Pauli blocking. There would just not be enough phase space to pack as much dark matter into these regions as you need in order to satisfy, for instance, the observations from galaxy rotation curves and so on. And that's what's called the Tremaine gun bound. And one can argue about the exact location of this bound. There are some astrophysical uncertainties, but the idea that you get is that anything below 100 electron volts is pretty firmly excluded by this. Now, what's also interesting about this plot is these hatched regions. Yes, there is this purple hatched region labeled pulsar kicks, and these gray hatched regions labeled 100 to 300 kiloparsec Fornax core. These are some very mild hints that may be interpreted as a signal for sterile neutrino dark matter, not with any with any significance that should give you sleepless nights, but there are these anomalies, and they can be interpreted that way. The pulsar kick anomaly, have you heard of pulsar kicks? So what's happening is when a supernova explodes and forms a neutron star, then these neutron stars sometimes get ejected at fairly high velocities. The most likely explanation for this is that supernova explosions are just highly asymmetric processes. So the nascent neutron star is radiating off neutrinos like hell, but it's radiating off those neutrinos in a highly asymmetric way, so it experiences a recoil, and that's what gives it this kick. But it isn't, or at least in 2014, it wasn't entirely clear if this recoil from the asymmetric anisotropic neutrino emission is enough to explain the large observed velocities at which some pulsars are shooting through the galaxy. And so the idea was, if there were sterile neutrinos, then along with the active neutrinos, the nascent neutron star would also produce sterile neutrinos. And they have a larger mass, so they give it even more recoil. And that would increase the predicted pulsar kicks. Here, 100 to 300 kiloparsec Fornax core. Fornax is, I think, one of the dwarf galaxies that accompany the Milky Way. And the structure of the core of that galaxy at that time was better fit if one had warm dark matter than with cold dark matter. But this is very much in flux, so I wouldn't trust this anymore without seeing confirmation from a newer paper. What still stands and what is interesting is this point here. I'm going to go into this in a bit more detail, but that's an analysis. It's actually the analysis from that paper from which I've taken the plot, where they've looked at X-ray data from galaxy clusters. So galaxy clusters also contain a fairly large amount of dark matter. It's relatively dilute inside the clusters, but it's just a very, very large amount because clusters are so huge. And when they are far away, they look like a point source anyway, no matter how big they are in reality. And they did this for a number of galaxy clusters, and they superimposed the spectra of all of these clusters adjusted for redshift. And they saw a mildly significant line here. And so this is a stereoneutrino mass of about 7 keV. So the line was at 3.5 keV. The jury is still out whether that is a real signal or whether this is some. Well, no, I think I'm sure it's a real signal. The question is if it's a signal of dark matter or rather a signal of some poorly understood atomic physics, for instance. It's an X-ray line after all. So atoms produce X-ray lines. We think we know at what energies atoms emit X-rays, but there is conditions in the universe where you can get lines that you would rarely observe at Earth. So depending on whom you ask, people have very, very strong opinions on this issue. Some very, very strongly argue that this must be something fundamentally new, and others argue very, very strongly that this can only be atomic physics. Well, so if the experts don't agree, then I guess we'll have to wait for more data. This would have been resolved if the Hitomi satellite had not exploded. So that was a bit of an unfortunate story. The X-ray observations on which this is based is like, let's say, the previous generation of X-ray telescopes. And there was a beautiful mission called Hitomi, which was successfully launched into space and which had X-ray spectrometers on board that had a much better resolution than the previous ones. And this would have helped to determine whether this line is of astrophysics, of atomic physics origin or particle physics origin, because it would have allowed to measure the precise shape of the line. And the dispersion of an atomic line is mostly given by collisional broadening and effects like that. Whereas the dispersion of a dark matter line is essentially given by the Doppler effect coming from the dark matter velocity distribution. And it would have been possible to measure this with Hitomi, but what unfortunately happened is, so while they were doing in-flight commissioning, at some point, some sensor on board of the satellite failed and made the computer believe that the satellite was spinning at a relatively fast rate. That wasn't true, but the computer tried to compensate. So it inadvertently put the satellite into a fast rotating motion until the solar panels flew off. And now I think there is going to be a replacement mission, but unfortunately we don't have this data yet. Otherwise we would have had it already. Right. But what I should also say about stereoneutrino production, you notice that this point here is far off the Dodelson-Wittrow curve. But as I already mentioned before, there's other production mechanisms that can also populate the region here to the left. And one of these production mechanisms is illustrated with these red curves here. That's what's called the Shih-Fuller mechanism. And the basic idea is you still do neutrino oscillations, but you postulate that there's a large lepton asymmetry in the universe. So significantly more neutrinos than antineutrinos, for instance. That's a possibility that cannot be ruled out. It's maybe not what we would naively expect. Naively, we would expect that the particle-antiparticle asymmetry in the leptons is roughly the same as the particle-antiparticle asymmetry in the baryons, which we measure rather precisely. But it can't be ruled out that the asymmetry in the leptons is much, much larger, and there are mechanisms to generate such a large asymmetry. And what this would do is it would change the behavior of this theta m, effective mixing angle. When we briefly discussed this before, I mentioned that in the early universe, it's mostly thermal loops that contribute to the change in the mixing angle in medium. However, if there is such a large lepton asymmetry, then there suddenly would be significantly more particles than antiparticles in the primordial plasma. And then even the tree level diagram that I had in my notes would contribute and would change the effective mixing angle significantly. Most importantly, the effective mixing angle would then have the possibility of going through a resonance. There might be a period during the evolution of the universe, excuse me, where the mixing angle becomes very, very large for a short amount of time. So you make sterile neutrinos very efficiently. And that's why with this mechanism, you can go here to much, much smaller vacuum mixing angles and populate also this left-hand parameter region of the parameter space. There's other mechanisms. I have a few slides on those. If we have time, we can talk about those too.
Joachim, there's a question on the chat.
Sure.
I'll read it out.
Yeah, thank you.
So Simon May, sorry, already a few minutes ago before you went to the slides was asking, is there any motivation for this version of sterile neutrinos besides dark matter?
I would say for this particular mass range, there is no strong motivation other than dark matter. I mean, there's nothing wrong with having a sterile neutrino in this mass range, but there's also nothing that points to that particular mass range. Right, so I promised you a somewhat more modern plot. So this is a plot from 2019. Unfortunately, the community cannot agree on whether to plot the mixing angle on the vertical axis and the mass on the horizontal axis, or the mass on the vertical axis and the mixing angle on the horizontal axis. So it's very confusing because this plot chooses a convention different from that one. But the mass range covered the mass range covered here is a subset of the mass range covered in the previous plot. That's when you have a limit, you choose, of course, the mass range where you can best present your own limit. The main thing here is, so up here, this red dot, this is this 3.5 kV X-ray line that I mentioned. And as you see, this is now already inside the constraints. So there are some observations that still see this line, but there are others that don't see it. And that makes the whole situation even more confusing. There's here, for the case of the Shih-Fuller mechanism, there's also a BDN constraint that was not plotted on the previous on the previous plot, and that would rule out anything below this black dash curve for the Shih-Fuller mechanism. Once again, there's other production mechanisms that would allow you to evade also this constraint. But if you believe that the production mechanism is oscillations, resonantly enhanced or not, then you're basically now tied to this region between the black dashed line and the X-ray limits coming here from the top. So you see that there's relatively little parameter space left. Now let's talk a bit about structure formation. I mentioned already a couple of times that sterile neutrinos would be warm dark matter, whereas the standard rule is that dark matter should be cold. Now this is one of the, and once again, not entirely up-to-date simulation of structure formation. But what you see is when you simulate the formation of cosmic structure, then you form these filaments. So this is like a slice of the universe. And you see that the initially almost homogeneous universe collapses into these filaments of high dark matter density. So the bright spots here are galaxy clusters, for instance. And this filamentary structure depends on what the mass of your dark matter is. So here's the outcome of 3 different simulations. The one up here is hot dark matter, 0.1 keV. So you can see there's hardly any structure forming. Over here is warm dark matter, and down there is cold dark matter. Now the warm and cold dark matter cases look much more similar to one another, but still you can see that in the warm dark matter case, this is more smooth, a bit blurred, and in general, a bit less structure. And that is a difference that can be constrained with observations, because we can we now have excellent surveys of galaxy and cluster counts out to very high redshift, covering a very large area of the space. So we can really check whether these filamentary structures kind of match what we see in the universe. Of course, we cannot predict the exact filaments that we are going to see, but we can predict how many filaments of a given size we expect to see, for instance. That's shown here, for instance. That's the so-called transfer function, which shows how the small fluctuations at early times relate to the large fluctuations at late times. You see here a strong dependence on the dark matter mass, especially at large K, which corresponds to small scales. So for cold dark matter, in this normalization here, there is as much structure at large scales as there is at small scales. And then for lighter and lighter dark matter, this transfer function cuts off, which means that structures that are smaller than a given scale cannot form anymore. Yeah, this is just a statement, repeating the statement that I just made. Here is another important observation that I didn't mention. Yeah, this is so-called Lyman alpha forests. So what this is, you know the Lyman alpha line. It's one of the atomic transitions in hydrogen. Now, because the universe consists almost exclusively of hydrogen, you can see this line from anywhere. However, if you're looking at stuff that's very far away, then the line is redshifted. So what you can do is the following. Take some very bright, very distant source, for instance, a quasar. Quasars are very active, very massive black holes that emit so much radiation that we can see them out to extremely large redshifts. So you use this quasar as a backlight. The quasar emits some kind of continuous photon spectrum. And then whenever these photons on the way to Earth travel through a cloud of hydrogen gas, the photons at the energy corresponding to the Lyman alpha line will be absorbed. So you see an absorption dip in the spectrum. Now, on their way to us, these photons are redshifted. So as they travel to us, the position of the Lyman alpha line inside their spectrum gets shifted again and again and again. So by looking at all the absorption dips that you see in your spectrum, you get an idea of where along the line of sight you have hydrogen clouds, or in other words, where along the line of sight you have matter, because the hydrogen usually follows the dark matter. So you know where there's a dark matter overdensity, there will also be a hydrogen overdensity, and you see this as a dip in your Lyman alpha forest. It's called a Lyman alpha forest because there's typically a quite large number of these absorption lines. And so you do this for a number of quasars, and this then allows you to do a three-dimensional map of where in the universe matter is concentrated, how large the concentrations of matter are, how far they are apart, and so on. So that, in a sense, it allows you to make a three-dimensional map of the universe. And then you compare this three-dimensional map of the universe to the predictions of your model. And that is shown here, for instance. The bright green curves here are the best fit, and the red curves here are the predictions of a warm dark matter model. And as you can see, this warm dark matter model does not explain the data as well as the fit, which is the best fit, which is more similar to cold dark matter. The horizontal axis in this plot is once again the scale, but scales here on the right being smaller than scales here on the left. And the vertical axis is basically a measure for the for how much matter there is at a given scale. And the different curves here, I believe, correspond to different redshift windows. Right, so this allows you to get pretty strong constraints, because with these Lyman alpha forests, you can probe the matter power spectrum down to relatively small scales. There is maybe some people will argue that there is a large theoretical challenge involved in setting these constraints, because when I said, well, hydrogen follows the dark matter, that's true at 0th order, but that's not true when you want to do precision physics. So Lyman alpha forests are what's called a biased tracer, which means the thing you observe, namely the distribution of hydrogen in the universe, does not faithfully follow the thing you're actually interested in, namely the distribution of dark matter in the universe. So you need to know this bias. You need to know to what extent the distribution of hydrogen differs from the distribution of dark matter. And that is something that involves n-body simulations and is therefore challenging. Okay, so now here's once again the plot that shows the X-ray line here, because I want to go into a bit more detail on this. Here's what this looks like when you look at the spectrum. The top here is the total X-ray spectrum. The bottom one here is the background subtracted one. And this axis here, around where my mouse pointer is, that's what's called the 3.5 keV line. Now you may argue how significant this is, especially when you look at the plot here on the top. You can argue how significant this is, but statistically, it's quite robust. It is a line. I mean, it doesn't look like a line here, but that's just because this is an incredibly blown up portion of the total energy range. So the width of this line is perfectly consistent with the resolution of the instruments that were used to obtain this. Well, and then the point is whether or not this can be due to atomic physics. Okay, now let me see what I should do first. Yeah, let's talk maybe a bit about alternative production mechanisms of stereometries. Unless you have more questions on these observational constraints, then I'd be happier to take questions instead. Yeah.
What is the
No, it's then. Oh,
Maybe you shout and I repeat the question.
no, it's just a basic question. How is the main explanation of the standard model for the 3.5 line?
Okay, so the question is, what is the main standard model explanation for the 3.5 keV line? So it is a top.
Just one sec. Is there someone who reserved the shuttle for 10:30 here in the room?
11:30.
11:30. No. Because there's a taxi. It's first already.
Just
Someone just ran out.
Okay, so the main standard model explanation is atomic physics, in particular so-called charge exchange reactions. Now, the problem with atoms in the universe are that they can exist in all possible ionization states. On Earth, all atoms are neutral, but in the universe, where matter is so dilute, if by any process you ionize an atom to an arbitrarily high ionization state, it's very unlikely that that atom will somewhere find an electron to fill up its electron shell again. So you have atoms in all ionization states ranging from completely neutral to fully ionized. Now, each ionization state has different X-ray spectra. In principle, we can measure those at Earth, so we can make a full catalog. But the problem is, well, yes, there are X-ray lines that are known in atomic physics that would fall into this range here. However, the intensity of different X-ray lines is typically correlated. For instance, if you imagine if you know the intensity of a 2p to 1s transition, then you can relate this to the expected intensity of, say, a 3p to 2s transition. Because it's the same atom, so the number of the atoms is the same, and the rates of the different transitions the relative rates of the different transitions is something you can compute. So the proponents of a new physics explanation for this will argue that the atomic physics lines that in principle could contribute here would also lead to X-ray lines at other energies where they are not seen. So if there was an atomic physics line here, they argue, there should be other, much more intense lines at other energies where we don't see them. And then others argue that the atomic physics models that they've been using are incomplete, that there are reactions, for instance, that are called charge exchange reactions, where two atoms meet and an electron goes from one atom to the other atom. This leads to, once again, new X-ray lines, and then people argue about whether their atomic physics models are complete or not. But that's what it boils down to. Do we understand the standard model X-ray lines well enough to be sure that there is no standard model X-ray emission in this region? Okay. Any further questions? Doesn't seem to be the case. So one production mechanism for this kind of dark matter that has gained in popularity a couple of years ago after it turned out that the oscillatory production was becoming more and more constrained is production in the decay of heavy scalars. Here is one particular model that was especially studied by Alex Meale and his collaborators, for instance. So what they are introducing here new sterile neutrinos N and a new scalar S. There is, of course, the kinetic term for both particle species. There is the unavoidable scalar quartic coupling, and there is the U-carbon coupling between the scalar and the sterile neutrino. So the idea is that the scalar is produced at early times via freeze-in through the scalar quartic, which is here at the end of the Lagrangian, and then eventually decays into sterile neutrinos. Now one can show that this produces the sterile neutrinos with a relatively cold spectrum. And this in particular helps evade the structure formation constraints, for instance, the constraint from Lyman alpha data. Well, here they have a relatively complicated parameter space plot, which I think I'm not going to go into detail on now. Another possibility is consider once again a fermionic dark matter candidate and a dark sector scalar. And we consider also a higher dimensional operator through which this scalar couples to the electromagnetic field strength tensor. What this does is it allows the scalar to annihilate into 2 photons. And it also allows the dark matter particle to annihilate into photons, to annihilate into 4 photons. But if the masses of these, if the relative masses of these particles are chosen in the right way, then to the detectors, this can still look like almost like an X-ray line. So that's basically an alternative explanation for this line where the relevant process is annihilation of dark matter and not decay. That's usually hard to achieve at these low masses. Typically, the annihilation rates are too low, but here it turns out that it works. Also not going to go into much detail here because I still want to discuss this type of plot. That's again a very busy plot. This is once again a version of the plot where the horizontal axis is the mass of the dark matter particle, the vertical axis is the coupling constant, respectively the mixing angle. And the different blobs here correspond to the preferred regions from different observations. Let's focus on the plot on the right in particular, because that's the one for sterile neutrinos. The one on the left is for this annihilating dark matter explanation. So here, let's see these yellowish regions. I think these are all different galaxy clusters. The green one is a specific observation of the Perseus cluster. That's a galaxy cluster relatively close to us. Chandra deep. So Chandra is an X-ray telescope. What deep means, I'm not entirely sure anymore. Here, M31 is observations of the Andromeda galaxy. But what you can see is that these different blobs, they don't really overlap as much as one would have hoped them to overlap. Moreover, there are these lines here. These are constraints from observations that did not find the 3.5 kV line. And you see that especially this one here, this is another observation of M31, that disfavors almost all of the observations here. So that's a bit of a confusing situation. And one could argue that this points more towards an atomic physics origin. Because in order to relate these different observations, well, they are basically related by our predictions for the dark matter density in those various astrophysical objects. So if this line was due to dark matter, then we could predict how strong it should be from a galaxy cluster, how strong it should be from the Andromeda galaxy, how strong it should be in the diffuse X-ray background, and so on. And what we observe, so the relative intensities of the line in those different regions do not really agree with the relative dark matter abundances in these regions. The proponents will say that this is all still okay and blah blah blah, but I think it is a bit worrisome. And of course, if this was just atomic physics, well, the element abundances, the ionization states of elements, and so on, that will be very different in different galaxies and galaxy clusters. So the relative intensities of an atomic line can be very different in different regions of the universe than the relative predictions for a dark matter origin. But this gives you an idea of where the status is, and that the data doesn't, in that sense, not really particularly strongly support the dark matter explanation of this excess. However, I think what's interesting is that we have these observations and we are really probing very relevant parameter space here, and that at least the simplest sterile neutrino production mechanisms can be conclusively probed in the very near future. Okay, now let's not go into details on this. This is once again about the annihilating dark matter model, but I'm not sure how much sense it makes to go into one specific model. Let me see. I see a number of things on the chat. Is this? No, okay, this is the question that I answered already. I think it's perhaps better if I use my last few minutes to comment a little more generally on why or why not sterile neutrinos may or may not be useful in particle physics. And well, when I defined the term sterile neutrino yesterday, I said a sterile neutrino is just a standard model singlet fermion. So it's a very simple addition to the standard model, and in fact, it's a very simple addition to any model. You can basically add a sterile neutrino to any model in particle physics. One may argue whether there is a particular reason to do so, but there's also nothing that prevents us from doing it. And in that sense, it's not unlikely that any new fermion that exists in nature will behave like a sterile neutrino, in the sense that it doesn't couple to standard model gauge charges. Then, of course, we have, from a theoretical point of view, no idea of where a sterile neutrino could be in terms of its mass. All the sterile neutrino literature is motivated by one observation or another and sets a mass range based on observations. There are the very light sterile neutrinos at the electron volt scale that aim to explain some anomalies observed in neutrino oscillation experiments. So there are some neutrino oscillation experiments that appear to see neutrino oscillations over distance scales that are too short for standard model oscillations to develop. So the typical oscillation lengths for standard model neutrinos at, say, energies of GeV are of order hundreds of kilometers. But there are some experiments that appear to observe oscillations over scales of only 1 kilometer. That's inconsistent with the standard model, but could be explained if there was a fourth mass eigenstate with a somewhat larger mass than the standard model mass eigenstates. Somewhat larger means electron volt scale or so. Now, once again, there are some experiments that see this, there are others that don't see it. So it's a very confusing situation in terms of the data. We don't really know where the data is pointing. There is an accumulation of anomalies that all appear to be pointing in the same direction. And then there is a number of exclusion limits that pretty firmly say no. So, and I should say that the data that point towards a new type of oscillation, they are in no way correlated. So these are completely different experimental technologies that are all pointing towards the same parameter region when interpreted in terms of sterile neutrinos. But once again, there's other experiments that very firmly rule out this possibility. Okay, then at the KeV scale, the motivation for sterile neutrinos could be dark matter. But once again, that's the only thing that makes us look at the KeV scale. There's no other motivation to look at that scale and not at any other scale. In recent years, people often have looked at sterile neutrinos at the MEV to GeV scale. In that literature, this is mostly called heavy neutral electrons. And the main motivation here is that that is a mass range that we can actually probe. There are some interesting proposals for experiments, typically based on very, very intense beams dumped onto a target in order to hopefully make sterile neutrinos and then observe the decays at a detector that's placed some distance away. So that's interesting in that sense because it's a region we can probe, and the hope would be that if there is a sterile neutrino there, that it may in one way or another be related to the generation of neutrino masses. However, this connection can only be made in somewhat non-minimal neutrino mass models. In the most minimal neutrino mass models, which is the seesaw mechanism, you have stereo neutrinos, but you have them at a much, much higher scale. At least a TeV, but maybe up to 10 to the 14 GeV or so. That's because in this mechanism, the active neutrino masses are basically determined by a ratio of a typical standard model mass scale, which is 100 GeV, and some very high mass scale. So you take 100 GeV over 10 to the 14 GeV, and that factor is then what suppresses neutrino masses to the level that we observe today. Now you can do this also at lower masses, but then one can argue how natural this still is, but naturalness arguments are always inefficient. And finally, another reason to look at these very heavy sterile neutrinos is the mechanism of leptogenesis, where essentially the decays of the sterile neutrinos in the very, very early universe go asymmetrically into particles and antiparticles, thereby explaining the particle-antiparticle symmetry of the universe. Once again, all these mass scales are motivated by observations. There's no particular theoretical guidance that one can give. Okay, I think my time is up. If there are still questions, I'm happy to answer them now. If there are questions later, feel free to get in touch by email. So yeah, thanks for bearing with me, and I wish you all a good trip home.
The last minute question for Joachim. Okay. Thanks to Joachim again. And stop it.